Hello, welcome to another video in vibration waves. Um, i- Ordinarily, we will start on this chapter on waves or traveling waves or progressive waves right after the midterm break. But because of a lot of things that happened this year, we are starting now. Okay, so this is very exciting part of the course. Things are moving, things are kind of a little complicated. We are things are moving in one way, but some other things are moving another way. Is interesting. Okay, so brace yourself. We're going to learn some new techniques, a new phenomena, interesting phenomena. I hope I can show you some of the phenomena by a demonstration. So the simplest and most basic type of traveling waves is a wave that can be written as a sine or cosine. Okay, so as far as the time variation is concerned, how the waves are oscillating, their oscillations are harmonic. So by harmonic, we only means one thing basically. We mean sinusoidal, sine or cosine or combination of the two of a single frequency. Okay, so we've seen the harmonic, right? I mean, simple harmonic oscillator is a vibration that has 1 degree of freedom, and here there will be many degrees of freedom, but every degree of freedom is oscillating with only one frequency, same frequency. Okay, and don't confuse that with normal modes or anything. It's nothing to do with normal modes yet, right? It's just a frequency with that's common to the oscillation in the system. And when I write it analytically, is going to be sine or cosine. Okay, so let's put some kind of physical sense to it. Suppose I have a string and I want to oscillate the string and let a wave be generated there. That's why we did the driven oscillator part, because we're going to learn how to generate wave which kind of progresses down the string, right? So here's this string which is taut, and on the other side fixed, and this side I'm going to oscillate it, and you can see, let's see, this is a t equal to 0. This color is t equal to 0. Let me write that down. So this is t equal to 0, and then this is t equals to t1, a little bit later time, and then a little bit later time still we have a t equals to t2. All right, so these have been drawn at 3 successive times. Couple of things I want you to notice is that as this pattern in the string gets different kind of shape, same shape, but at different places, and the particles of the string. So when we look at I look at this particle, this string, okay, where is it at t2? At t1 it's actually gone down, it's moving down, and at t2 it moved further down, right? And later on it's going to move up a little bit and like that. So it's going down in this time. How about over here? Over here the same situation, going down. But when we look at over here, it used to be here, and then it moved up, right? And then it moved up. So if you look at various slices at various places along this string, you find the particles are moving up and down. They're not going sideways. This is a so-called transverse wave. We call it transverse wave. So while this pattern, this wavy thing, and this pattern is moving that way, the particles are moving up and down, and they make a certain amplitude oscillation, and that's why these two angle be 90 degrees. We call it transverse wave. When we study sound in air, we will find that this is not the case in sound in air. The particles will be also oscillating the same direction the waves are moving, and that's harder to draw, and that's why I didn't draw it. Okay, but there, the wave direction and the particle oscillation direction would be along the same line, and this kind of wave will be called longitudinal waves. And we will study this study of transverse and longitudinal property of waves. That part of the wave phenomena is called polarization. We will study that later in more detail. This is just an introductory lecture. Okay, now here the displacement from equilibrium is the property that's oscillating, right? Displacement from the equilibrium, how much the particle has moved in time, so like this distance. So that's the psi. Over in the sound wave, it will be displacement of the equilibrium also. There also we have another particle pressure change from the ambient pressure. That's another way to look at sound wave. In electromagnetic wave, it will be electric field. So there's no electric field, and when the wave is there, the electric field is there, or magnetic field is there. So that will be electromagnetic waves. Same language you can use. How about the quantum wave? Quantum wave will be same wave function, no wave function, and then there's a wave function has some value. So let's use the same kind of language. So instead of calling it y, we can call psi of x and t. So if this is the, say, x coordinate, and this is we're looking at that point, so that's motion is going to be between this and this. So this particle oscillates with plus a and minus a. We can choose time 0 so that it's at this place. That will be psi 0 at 0, psi at x equal to 0 and t equal to 0. That kind of says where my t equal to 0 is, where my x equal to 0 is, right? So the choice of this, say this for some reason, for simplicity, for instance, we can say let's look at a wave that's a over here. Well, this you can see this, if psi of x equal to 0, t equal to 0 is a, and it's going up and down with frequency omega. So we can say psi of 0 at some other time is just a cosine omega t. See, as for the particle, so this is the particle at x equal to 0. As far as that guy is concerned, it's just a simple harmonic oscillator back and forth, and we assume this for the sake of simplicity and see what happens. The question is, can I say what's happening at, say, some x value at some time t? How can I relate that to what's happening at over here? Because this thing is moving in a very predictable way, so I should be able to relate it. Turns out really true that we can relate it, and here is a way to think about it. There are other ways, but this is I like really cool. This is cool. So t equal to 0. When you look at this, let's go back over here. So this was, look at this over here. The value happened at t equals to t1, but that value was actually in the wave a little bit earlier, right? This is a little bit earlier in the space. little bit later in time, little bit later in time is a little bit earlier in space. Okay, let me make sure you understand this. This diagram is telling me that where I am at a little bit later in time is where I was a little bit earlier in space. So I was here, which is same level. This, you can translate that to where I am here now at this time. If I go back in space, then I have to go back in time also. So we define what is called retarded time. Retarded time. So if you've taken the modern, you know retarded time. But here it's really cool. So right now time is t. So we say I have to go back x distance to get to the origin, and I'm traveling with the wave speed vp. So this wave is traveling at some speed vp. We're going to call it vp instead of v. You'll see why in just a minute. P is for phase velocity. So I have to go back this much in time to get to the same level I was here. Is going to be exactly the same over there. So if I want to get this, I need to go to the origin, and there I need to go to the retarded time, evaluate the retarded time. But the origin at all times is known to me. That's the one I assume right from the get-go. Okay. That's going to be wave. That's the vibration of the particle at the origin. So I can just plug for t, I can use retarded t. And we already started, that will be expressing like that. And so you can see that if I can multiply this out, I get my omega t minus kx. This is the kx, right? And we have seen this. This has to do with frequency, and this has to do with the wavelength. So we can have a regular frequency defined this way. This will be period of the wave, and this will be the wave number of the wave. So this is called wave number. And wave number is related to how many waves will fit in 2 pi radian. Okay, and okay, so this is, all of these are old knowledge. Let's write this down in a standard notation, which is a cos kx minus omega t. And I've kind of set the phase constant at 0. That's basically choosing x and t origins. So this part, which is the argument of cosine, we'll call it phase function or just phase. We can see it for a particular wave number and frequency. It depends, a function of x and t. So if I want to say I'm looking at a particular phase value, and for that phase value, when will I get that? You know, how fast x and t have to change in order to be hit the same phase constant, same phase value. So I can set 0 or anything between 0 and 2 pi, and demand that this be a constant. So these are times and positions at which I'll get exactly same phase wave at the same phase value. Well, we can take a differential of this, and you can see that x and t actually have, them both are moving, right? Both are changing. So the speed dx dt tells me the phase, a constant phase speed, and that's called phase velocity. So this is the way, this is the speed which the wave must move. This is a single frequency wave, and this sinusoidal wave, we call it phase velocity. We are going to encounter another kind of velocity, which will happen in a more realistic waves. It's called groove velocity. Single frequency waves are nice to study. It's a good model for a lot of systems, but nearly impossible to create them. We will study what is called when we put a lot of waves together and make it. Suppose you have a wave which frequency is not a single frequency, but suppose power in the wave was kind of distributed, not just single frequency, but distributed over frequencies. Then which you can see which omega and which k I should use to define what speed the wave will be going. Maybe for any omega, and you take its omega over k is constant for your wave, then the phase velocity is the same as what we will describe later, group velocity. But if omega and k do not have a constant relationship, omega over k is not constant, then if you have a whole bunch of omegas, then how do I define a velocity at which, for instance, energy travels? So we saw how the wave travels for a single frequency. We can ask question at what speed the energy in the wave travels. That's kind of a strange question, but we will ask that question, and that will lead us to a more physical velocity called group velocity. We're going to talk about that in another video. Okay.